Hello friends, in this lecture we will look at quantization. Recall that analog to digital conversion of a signal is a two-step process. The first step is to discretize the signal in time. This is achieved through sampling, and the second step is to discretize the signal in amplitude. This is achieved through quantization. We have already seen the process of sampling. Let us now start looking at quantization. In this lecture, we will look at the definition and mathematical representation of quantization and Midtread and Midrise type of uniform quantizers. So let us understand what is quantization. Let there be a signal m of t, which is a continuous time and continuous amplitude signal. That means which is an analog signal, and that this signal has been sampled at integer multiples of some sampling interval ts. Let n times ts be a general sampling instant, and the corresponding sample value is m of nts, which belongs to a continuous set of values. Now mapping this value to a discrete set of values is termed as quantization. For example, suppose we decide to have 5 quantization level for a certain signal as -2, -1, 0, 1 and 2. Then any value falling between say 0.5 to 1.5 will get mapped to 1. Say for example 1.32 will get mapped to 1. Similarly 0.95 will also get mapped to 1. A value which is say 2.16 will get mapped to 2, and so on. Clearly, this is a many-to-one mapping, and therefore it leads to an error, which is called the quantization error. We will look at this error in another lecture. Mathematically, quantization can be represented as V equal to G of M, where M is the sample value that belongs to the continuous set, m of nts. G is the quantization function which maps m from a continuous set to a discrete set, and V is the quantization level or the quantized value which belongs to that discrete set. Let us, for example, consider a 5-level quantizer which is used for quantizing a signal whose amplitude ranges from say some -5 delta by 2 to +5 delta by 2. Delta is some number which we'll call step size. So there are, you can see here, 5 quantization intervals: -5 delta by 2 to -3 delta by 2, -3 delta by 2 to minus delta by 2, minus delta by 2 to plus delta by 2, plus delta by 2 to 3 delta by 2, and 3 delta by 2 to 5 delta by 2. There are 5 quantization intervals. Each interval is of same length, and we define the center point of each interval as the quantization level. This is the input m, and this is the function g of m, which is v, the quantized level. So whenever m takes a value in the range, for example minus delta by 2 to delta by 2, its center point 0 is the corresponding quantized level. If a value falls between delta by 2 to 3 delta by 2, all those values, all those infinite possible values are assigned a single quantization level, delta, as shown here. So the center point of any interval is taken as the quantization level. So clearly, if there are 5 quantization intervals, there will be 5 quantization levels as shown here: -2 delta, minus delta, delta, and 2 delta. Clearly, the quantization characteristic is a staircase function, and in this example, if you observe closely, at the center, when m is 0, the quantization characteristic is flat, and that is the reason why this type of characteristic is called mid-trade quantization characteristic, or the corresponding quantizer is called mid-trade quantizer, because the term trade literally means the flat portion of this tape. Indeed, whenever there are odd number of quantization levels, the corresponding quantization characteristic will always be a mid-trade characteristic. This range from minus 5 delta by 2, the minimum sample value, to the maximum sample value 5 delta by 2, this range is called the dynamic range of the quantizer. Take another example. Suppose we have 4 quantization levels and 4 quantization intervals correspondingly. Say minus 2 delta to minus delta to 0, 0 to delta, and delta to 2 delta. These are the quantization intervals that our sample values can take values from minus 2 delta to plus 2 delta. Again, we assign the center or the middle point of each quantization interval as a quantization level. Say if the signal value falls between 0 to delta, then we assign it one value, what is delta by 2. Similarly, if the sample value is between delta to 2 delta, it is mapped to a value 3 delta by 2, which is the corresponding quantization level, and so on. Clearly, there are 4 quantization intervals here and 4 quantization levels as well. What are the levels? Minus 3 delta by 2, minus delta by 2, delta by 2, and 3 delta by 2. So 4 quantization intervals, 4 quantization levels. So always remember the number of quantization intervals and number of quantization levels will always be same, because for every interval we have one quantization level which is the center point of that interval. Incidentally, you observe here that at the center, when m is 0, the quantization characteristic is rising from a negative value to a positive value, and therefore this quantizer, a quantizer with this characteristic, is called a mid-rise quantizer. Indeed, whenever there are even number of quantization levels, the quantization characteristic will be mid-rise type. So for odd number of quantization levels, we have Midtread quantization characteristics, and for even number of quantization levels, we have Midrise quantization characteristics. Now there is a definite relationship between the dynamic range of the quantizer and the number of quantization levels. You can see another thing here, whether you take this example of Midtread quantizer or that of Midrise quantizer, the length of the quantization interval is same, which is delta, minus 2 delta to minus delta, the length is delta, minus delta to 0, length is delta, and so on. Or otherwise you see the difference between two successive quantization levels, delta by 2 and minus delta by 2, the height is delta. Similarly, 3 delta by 2 and delta by 2, the height is delta, right? So you see, whether you look at the length of the quantization interval or the height of the step size here, it is delta, it is uniform, and that is the reason why such a quantizer or such quantizers are called uniform quantizers. Sometimes we also need non-uniform quantizers. We will discuss them separately. So let us continue with the discussion on uniform quantization. Suppose the dynamic range of the signal, which is the difference between the maximum positive peak value and the negative peak value. We assume that the peak positive amplitude is mmax and peak negative amplitude is minus mmax, so that the dynamic range is 2 times mmax. Then the number of quantization levels, which we denote by L, is given by 2mx by delta, the dynamic range by delta, where delta is called the step size. You can see that whether you look at the length of the quantization interval, it is delta, or whether you look at the distance between two quantization levels, it is also delta, and therefore it is called a uniform quantizer. So L equal to 2mx by delta, or equivalently step size can be computed in terms of L as 2mx by L. Let us verify this through an example. Suppose we talk about a quantizer which is used to quantize a signal with range from minus 2 delta to plus 2 delta, that is its dynamic range is 2 times 2 delta, that is 4 delta, and the step size is delta. So 4 delta by delta equal to 4. So there are 4 number of quantization levels as we have seen in the example already. That's all for this lecture. Thank you.